Hi everyone. This is just a quick primer or tutorial on net torques and um, how they can, when you have a net torque that doesn't add up to zero, it can cause an angular acceleration, much like force causes an acceleration when you have a net force. So this is just a quick primer on this, getting to a quantity that's called moment of inertia and kind of wrapping up the big idea for today. Then I'll do some example problems for you. Okay, in some other videos. All right, the moment of a quantity, you've probably been wondering, we've been hearing this word moment of a quantity, is the effect of that quantity about an origin, so which is some distance away from that origin r. So kind of as we've learned, the moment of force is called a torque, okay, where torque is r cross f or rf sine theta. So the force is at a distance r, okay, located about some origin O, and we've already learned that that force acting about that towards an origin O can be affected by the distance the force is away. So you can increase torque by increasing the lever arm R. You can increase the torque by increasing or decreasing the force. That has the effect on changing the torque. Or you can also change the angle that the force is applied at. All of those things would change the net effect of producing a torque. Okay, we also learned that that's a vector quantity. All right, it can be either clockwise or counterclockwise rotation. So just like a net force causes an acceleration or a change in the velocity, a net torque causes the change in the angular acceleration or the change in the angular velocity. So in the F equals ma equation, notice that there's also the m. All right, the change in the acceleration is resisted by the object's inertia or mass. That's the first law. And so likewise in rotational motion, we should expect that same type of a thing. Objects just won't rotate freely, right? Otherwise a small torque would produce an infinite acceleration. So in any case, then if you think about it, there's going to be some type of effect of mass rotationally. And that's called rotational inertia, or the moment of inertia, because it's the effect of the mass located at a distance out some distance away from the origin. And that position has an effect on how hard it is to rotate something. So the moment of inertia is affected by mass and its location about an origin located a distance r away. It affects how hard it is to swing or rotate something. So the further away a mass is located from the point of rotation, say on a stick that you're trying to swing, for instance, the harder it is to get swinging. That's why when you choke up on a bat, you can swing the bat, you can get the bat up to speed quicker, you know, in either baseball or softball. You can try this little experiment here. So let's say we take the pencil about the middle. How the mass is distributed about the point of rotation also has an effect. So here, the mass is located even side. If you think about the center of mass of the pencil, here and here about this point of rotation, and you can like try to swing your pencil like rotating a baton about its center. Okay. Now, if you simply move all of that mass out here, so it's further away from this point of rotation, and you try to swing your pencil like this, you can feel that it's harder to get moving and it's harder to stop. So how the mass is distributed from your point of rotation also has an effect on the how hard it is to get to rotate. So there's all sorts of methods in calculating this, so we're going to be taking a look at that coming up over the next day. But let's take a look at the general equation for the net torque, and let's take a look at how we can get there from our F equals ma, our second law equation. So beginning with F equals ma, we know that to produce a torque, we can simply multiply our force by r, if we think about it just in the simplest sense, right? And so I multiply r times F, I can also multiply then the ma times the r, right? So rotationally, we know that the a, you've learned that the linear acceleration can be expressed as the radius times the angular acceleration of the rotating object. So I'm going to take the a in this torque equals r times ma equation now, from rf equals rma, right, and replace that acceleration with the rotational term r alpha. And what comes out of that, we can see as we get this new term, the torque is equal to r squared times m times alpha. So alpha is the angular acceleration, and a net torque is what causes that angular acceleration. So this quantity here, r squared times m, describes not only the mass, right? It's what we call the inertia of the object, but also the effect in the equation of its position r, a distance away from the origin. And so r squared m is defined as the rotational inertia about some origin, right, of the mass. And so if it's a point mass, right, if it's like a small ball bearing or something located out and you're trying to get it moving about O, maybe it's attached to a string or something like that, that point mass, that is the formula for the moment of inertia for a point mass. It's just the mass times its distance away from the origin squared. So you can see that in order to get an object angularly accelerating, there's two factors that determine how hard it is to get rotating, the resistance to rotation. The mass itself, which is what we know as the regular inertia, but also the square of its position. So that's a huge effect, right? You square the square of the position. So if you double the distance away, it would be 4 times harder to get moving for the same applied torque. That's huge. So we have to affect, where the position of the mass is and how that mass is distributed has a big effect on how hard it is to get an object rotating with a net torque. So we have to consider both those quantities now when we think about net torque and the angular acceleration. So if we put that into the equation, the overall like F equals ma type equation for rotation is that a net torque is equal to the rotational inertia times the angular acceleration. So I for a point mass is pretty easy, okay? It can be calculated, or if it's a complex shape, generally you need symmetry or you need arguments from calculus to be able to figure out what it is. So we're not going to worry about that in this video or beginning problems on how to find these values for the moments of inertia from calculus. There's a few simple ones we'll do coming up, probably tomorrow. But for today, you'll want to be able to use this chart and just start getting a feel for the problems about what is the object you're trying to rotate. So for instance, a hoop or a cylindrical shell, it's also kind of easy to understand because a distance r, all the mass of the thin hoop is located the distance r away. So just like a point mass where the rotational inertia is mr squared, because all the mass of the hoop is located the same distance r away from the center of rotation. This might be like a bike wheel, for instance, or a pipe or something like that. Spinning, mr squared is the same rotational inertia. But if you take a look at something like a solid cylinder or a disc, if you think about it, there's mass which is out here further, mass which is in closer. So how do you figure out like what the position is, right, to use for the moment of inertia? Now for a solid disc like this, it might be intuitive. Since about half the mass is out here and half the mass is in the middle, the moment of inertia is 1/2 mr squared for a solid cylinder or a disc. But it's maybe not quite as intuitive for something like a rod. So if you look at a thin rod, like the pencil about the center, okay, a pencil about the center, rotating it like this, you can see that the moment of inertia is 1/12 m times the length of the rod squared, okay? Whereas if you take that exact same thin rod and rotate it about the end, then it's 1/3 ml squared. So notice 1/3 ml squared is 4 times bigger, right, than the 1/12 ml squared. So that has a huge effect if you try to rotate a stick like this or rotate a stick like this in terms of how hard it is to get going for the same rotation. So these are the most common shapes. And so a solid sphere, a thin spherical shell, so this might be like a basketball, or this might be like a bowling ball. So depending on how that mass is distributed as it's rolling about the center or trying to get to rotate about the center, that has an effect. So when you use the equation and you're doing problems, you'll have to look it up in the table until you probably will have them memorized. And then for tomorrow, we'll learn how to start doing a few of these by calculus. So, and you don't have to be able to do all of them by calculus for the C exam, but it's good to get an overall idea of how that's done. All right, so now that's the big idea. Let's apply this to a few different problems.